Hi, future GISPs. I'm going to teach you everything that I learned to easily pass the GISP exam so that you don't have to spend years reading textbooks, getting degrees, paying for prep courses, and searching the internet for information like I did. In this video, I'm going to teach you everything I learned about field data collection. Field data collection is the second section under the data acquisition category of the GISCI Geospatial Core Technical Exam list of knowledge categories. Let's get started with section 402, field data collection. Field data collection is mostly done using two technologies, GNSS and surveying. First, I'll go over GNSS. The Global Positioning System, or GPS. The first satellite positioning system, Navstar, is called a GPS. GPS uses the WGS84 geographic coordinate system. A Global Navigation Satellite System, or GNSS. GNSS is the generic name for all satellite positioning systems, including Navstar and others. GNSS is used for tracking, navigation, field to digitizing, and surveying. GNSS can calculate the coordinates for a location by triangulating signals from 3 to 4 satellites. 4 satellites are required to calculate an accurate location quickly. GNSS has 3 main components: a satellite segment, a control segment, and a user segment. The satellite segment consists of satellites orbiting Earth and transmitting locational signals. The control segment consists of tracking, communications, data gathering, integration, analysis, and control facilities. The user segment consists of GNSS receivers. Navstar. Navstar is the GNSS, or GPS, system of the United States. Navstar has 21 active satellites and 3 spares distributed among 6 offset orbital planes. Every satellite orbits the Earth twice daily and is above the horizon for 8 or more hours each day. Satellites are controlled by a set of ground stations. GLONASS. GLONASS is the name of the Russian GNSS system. IRNSS. IRNSS is the GNSS of India. Galileo. Galileo is the European Space Agency's GNSS. The Compass or BeiDou system. The Compass or BeiDou system is the GNSS of China. An almanac. An almanac is the data broadcast by satellites about the satellite's status and location. A range distance. A range distance is the distance between 2 objects. For GNSS, the range distance is the distance between the satellite in space and the receiver on the ground. GNSS signals travel at the speed of light. The range distance for a GNSS measurement is calculated by multiplying the speed of light by the travel time. A receiver can instantly calculate its location from range distances from 4 satellites. A receiver. A receiver is an electronic device that records and processes data from satellites to determine three-dimensional positions. A range pole. A range pole is an extendable pole on which a GNSS antenna is mounted. A range pole improves accuracy and reduces multipath signals. A laser rangefinder. A laser rangefinder may be attached to GNSS receivers to improve field data collection. Laser rangefinders are used in conjunction with an integrated electronic compass which measures angles. These tools allow a GNSS operator to collect several positions from one location. GNSS height. GNSS typically measures height above an ellipsoid, not above a geoid. Orthometric height, or height measurements above a geoid, can be calculated by referencing a nearby control point. GPS signals. GPS signals contain the location of the satellite and the time at which the signals were sent. Code Division Multiple Access, or CDMA. Code Division Multiple Access is the technique of embedding signals within signals. All GNSS satellites transmit signals at the same frequencies. Signals are separated into channels. Many types of data from different sources can be sent on the same frequencies used by GNSS receivers. This is possible due to the coordination among different GNSS systems. Coded division multiple access is also used in cellular phone communications. Carrier phase signals. Carrier phase signals are more accurate than coded phase signals, but take longer to calculate and require more expensive receivers. Carrier phase signals carry coded signals. Coded signals. Coded signals are less accurate than carrier phase signals, but faster to use, and receivers that utilize coded signals cost less than receivers that utilize carrier phase signals. Coded signals are modulated from the carrier phase signals. Carrier signals. L1 and L2 bands carry most of the signals used by GNSS receivers. There are other experimental and secret bands. The L1 band carries the CA and P codes. The L2 band carries just the P code. The CA signal. The CA in CA signal stands for Course Acquisition Code. The CA signal is transmitted by all satellites. It is comprised of an L1 carrier modulated by a CA code. CM and CL signals. CM and CL signals are modulated on the L2 carrier. CM stands for civil medium. CL stands for civil long. The I5 and Q5 codes. I5 stands for in phase. Q5 stands for quadrophase. The I5 and Q5 codes are modulated in the L5 carrier. They are independent but synchronized. Megahertz. Megahertz measures millions of cycles per second. The Standard Positioning Service, or SPS. The Standard Positioning Service is a free GNSS service that uses the CA code to calculate positions. The standards are for satellite signals, not for receivers. The Standard Positioning Service requires signals to generate accuracy of 7.8 meters or less. The Precise Positioning Service, or PPS. The Precise Positioning Service is the GNSS service reserved for military use and authorized civilian users. It uses the P code, which is modulated over both L1 and L2 carriers. Consumer and recreational grade GPS. Consumer and recreational grade GPS has 10-meter accuracy and uses one frequency, the CA code from the L1 frequency. Survey-grade GNSS. Survey-grade GNSS receivers can reliably produce 10-centimeter accuracy. Survey-grade GNSS uses two frequencies, L1 and L2, to correct signal distortions caused by ionospheric delays. Military-grade GNSS. Military-grade GNSS reliably produces 1-meter accuracy. Military-grade GNSS uses two frequencies, the L1 and the L2. GNSS errors. GNSS errors are caused by errors in the satellite position data, errors in the satellite atomic clock or receiver clock time, ionospheric delays in signal transmission, multipath signals, and the satellite orientation. GNSS measurements can be improved by averaging multiple position fixes, using dual frequency receivers that collect information on multiple GNSS signals simultaneously, by setting a low signal-to-noise ratio, which will ignore signals with high noise, which reduces multipath signals, by using differential correction, and by setting a low PDOP threshold. Signal-to-noise ratio. Signal-to-noise ratio compares the level of a desired signal to the level of background noise. A ratio higher than 1:1 signifies more signal than noise. A higher signal-to-noise ratio indicates a more reliable signal. A signal strength threshold can be set on a receiver to eliminate multipath signals. Lower signal strengths will increase the amount of measurements recorded, but increase errors. A user range error. A user range error is a calculation of ranging accuracy. It is the fundamental performance parameter of GNSS that describes the total error that affects the distance measurements between a satellite and a user's receiver. It's the square root of the sum of the squares of the individual biases that contribute to the error, including atmospheric delay, satellite almanac inaccuracies, receiver noise, and multipath signal frequency. User accuracy. User accuracy is how close the device's calculated position is from the truth. It is expressed as a radius. The positional dilution of precision, or PDOP. Positional dilution of precision describes how good satellite configuration is for collecting accurate points. PDOP ranges from 1 to 20. A lower PDOP is better. 5 or less is considered good. PDOP improves if the satellites are spread more evenly through the sky. The PDOP signal strength threshold can be set on a receiver. A higher threshold will increase the number of fixes recorded, but lowers accuracy. Differential positioning. Differential positioning uses information from two receivers to remove range errors and improve accuracy. A base station. A base station is a stationary receiver at a known location. A base station is used to estimate range measurement errors and improve the accuracy of measurements. Real-time differential correction. Real-time differential correction requires a communications link between the base station and a roving receiver. Corrections are calculated from the base station and applied in real time. Real-time kinematic, or RTK. Real-time kinematic GNSS is used for high-accuracy GNSS location measurements. It uses a dual-frequency station and a rover. RTK uses differential correction as well as other improvement techniques to achieve centimeter-level accuracy for surveying. There is no uniform definition for what constitutes an RTK system across the field of GIS. RTK just means a highly accurate GNSS measurement system. A moving base station. A moving base station is when the base station is on a moving vehicle. Networked transport of RTCM via Internet Protocol, or NTRIP, NTRIP. NTRIP is a subscription service that provides corrective GNSS data through a wireless connection. This method requires a constant internet connection and a subscription to a local NTRIP service provider who will have an infrastructure of fixed base stations. The main advantage of NTRIP is that it uses a network of RTK base stations that are already in place and therefore has no range restriction. A satellite-based augmentation system. A satellite-based augmentation system is a system that obtains high accuracy by receiving differential correction data from stations around the United States and sending that data to the receivers to correct measurements. There are many satellite-based augmentation systems in place. The most advanced satellite-based augmentation system in the United States is the Wide Area Augmentation System. The Wide Area Augmentation System, or WAAS. The Wide Area Augmentation System is an air navigation aid developed by the Federal Aviation Administration. It uses a network of ground-based reference stations to measure variations in the GPS satellite signals. Corrective information is sent from reference stations to master stations to Wide Area Augmentation System satellites to Wide Area Augmentation System enabled GPS receivers. The Wide Area Augmentation System specifications require at least 7.6 meter accuracy 95% of the time, although accuracies are usually much better than a meter. A virtual reference station. A virtual reference station uses a network of reference stations that monitor GNSS signals and log corrections for reference. Data from the virtual reference stations and roving receiver are fed to control centers that perform corrective calculations. Many state governments are building virtual reference station networks. A continuous operating reference station, or CORS. A continuous operation reference station is a GNSS reference station minimally composed of a GNSS antenna, a GNSS receiver, data storage, and power. Continuous operating reference stations are managed by the National Oceanic and Atmospheric Administration. There are over 2,000 continuous operating reference stations. They provide information for differential correction GPS systems. Post-processing differential positioning. In post-processing differential positioning, measurements from the base station and receiver are downloaded to a computer after collection and corrections are processed. Post-processing differential positioning can't be used for navigation. Precise point positioning, or PPP. Precise point positioning is an alternative to differential correction. Precise point positioning performs high accuracy measurements by taking long observations over tens of minutes or hours. Those were most of the concepts that you could encounter on the GISP exam about GNSS or GPS. Now let's go over surveying. Surveying determines the locations of points by measuring distance and angles to other points. A triangulation survey. Triangulation surveying uses a network of interlocking triangles to determine positions at survey stations. Triangulation surveying was used prior to satellite positioning. Triangulation surveying utilizes the concept that the distance of a side of a triangle can be determined by knowing the distance of another side and the angles between the sides. Plane surveying. Plane surveying is surveying on a planar or flat surface. Coordinate geometry, or COGO, COGO. Coordinate geometry is used to draw points, lines, and polygons using survey points and measurements. Coordinate geometry measurements consist of a starting point, called a station, and a list of directions called bearings to subsequent stations. A traverse. A traverse is a series of connected lines that start at a control point. A traverse is the basic operation performed in coordinate geometry. Benchmarks. Benchmarks are known points across the United States with exact locations. They usually consist of a brass disc embedded in rock or concrete. Benchmarks are maintained by the National Geodetic Survey of the National Oceanic and Atmospheric Administration. Benchmarks are often used as control points. Azimuth angle. Azimuth angle is measured in a clockwise direction from 0 to 360 degrees relative to grid north. A bearing. A bearing specifies angles from 0 to 90 degrees by stating N or S for north or south, a measurement of degrees, and E or W for east or west. A transit. A transit is a survey instrument used for measuring horizontal angles. It has a telescope that can flip over for backsighting and doubling of angles for error reduction. A theodolite. A theodolite is a survey instrument for measuring horizontal and vertical angles. It consists of a telescope mounted on a horizontal and vertical axis. A theodolite is lightweight, easy to use, inexpensive, and doesn't require a power source. A total station. A total station is a survey instrument that combines the functionality of a theodolite with an electronic distance measurement device. It emits laser pulses to an accompanying prism to measure angles and distance. A total station only needs one person to operate it. A total station has a microprocessor that can store, display, and transfer data to an accompanying computer. A total station can be integrated with GPS, GIS, or BIM technology. Total stations are expensive. Electronic distance measurement, or EDM. Electronic distance measurement is a method of determining the length between 2 points using electromagnetic waves or lasers. EDM is commonly performed by total stations. The angle of deflection. The angle of deflection is the angle between a line and the prolongation of the preceding line. It is recorded to the right or left of the preceding line. Angle of deflection is used in surveying. Building Information Modeling, or BIM. Building information modeling is the generation and management of digital representations of the physical and functional characteristics of buildings and other physical assets. The field collection process should include 6 steps. First, determine what needs to be collected, inspected, or surveyed. Second, determine how it will be collected. Third, perform sample collections. Fourth, review sample collections and adjust methodology. Fifth, plan location and timing. And sixth, start collection. The Public Land Survey System, or PLSS. The Public Land Survey System is a standardized method for designating and describing land parcels in the U.S. Nearly all land outside the original 13 colonies uses the PLSS. The PLSS is not a coordinate system, but is often used as reference points for parcel surveys. The PLSS divides lands into 6 square mile townships. Each township is subdivided into 36 square mile sections. Each section is divided into quarter sections that are a half mile long or 16th sections that are a 16th of a mile long. Meets and bound surveying. Meets and bound surveying was the most common way of surveying before the public land survey system. Meets and bound surveying describes parcels relative to features on the landscape. Those descriptions are supplemented with angle or distance measurements. Now you know everything that I learned about field data collection to easily pass the GISP exam. Don't forget to thumbs up and subscribe to my channel so I can keep helping people pass the GISP exam and achieve the rewarding careers in GIS that they deserve. You can also find everything I learned to pass the GISP exam in my book, The Ultimate GISP Exam Study Guide, available on Amazon. My study guide is an easily understandable, comprehensive, graphical, all-in-one resource for passing the exam. You can find the link to my study guide in the description below. Thanks for joining me, and congratulations in advance on passing the GISP exam.